Today we're going to be talking about conservation laws and how they apply to physics and astronomy. So to review what we talked about last time, Newton discovered the laws of motion and gravity, and next class we'll come back to his theory of gravity and how it works on astronomical scales. And the big insight was that whatever laws describe motion on Earth have to be the same laws that work out in space. The three laws of motion that he came up with were inertia, or an object at constant velocity. An object moves at constant velocity if there's no net force. Then we defined what a force was. For this class, we'll just say it's mass times acceleration. And then Newton's third law is that for every force, there is an equal and opposite reaction force. So using those three laws, let's see if we can answer this question. So a car and a large truck have a head-on collision. The statement is that the force on the car is equal and opposite to the force on the truck. Is that true or false? Yeah, so this is true. So this is a consequence of Newton's third law. So for every action, there's an equal and opposite reaction. Even though the truck is bigger, it experiences the same force because it's the same collision that's happening. We'll talk about, there are some differences for the truck that we'll touch on in a minute. These conservation laws that we're going to be talking about are very important just in general for how the universe works, but also for how astronomy works. So we have these planets that are spinning on their axes and they're rotating about the sun, but why do they keep doing that? Does that require energy? The Earth doesn't have like a propulsion system that's pushing it along in its orbit, so why does it keep orbiting? And then where do objects get their energy from? The first conservation law that we'll talk about is conservation of momentum. So last class we saw momentum was the mass of an object times its velocity. And as a consequence of Newton's second law, if there's no external forces acting on an object, then its momentum has to be conserved. And when two objects interact with each other, or as we'll see in the example in a second, if they hit each other, then their exchange of momentum is governed by Newton's third law. So conservation of momentum is important when there's no forces or no external forces, and then it's also important for things like collisions. So let's do an example. So you're playing pool and you're trying to hit the 8-ball in the pocket. When you're playing pool, you have to hit the cue ball into whatever ball you're trying to hit. And so this is a collision problem. So we're saying that we would like the 8-ball to travel 2 meters per second towards the pocket. And after the collision, we don't want the cue ball to end up in the pocket, or else that's a scratch and you lose the game. So we want the cue ball to move in the opposite direction after it collides with the 8-ball. So what speed do we need to hit the cue ball in order for this situation to occur? So what conservation of momentum allows us to do is just write a very simple statement. Whatever momentum we start with has to be the same as the momentum that we end with. And remember, we defined momentum as mass times velocity. So what we're going to do, we have two objects. We're going to track their mass and velocity before the collision and after the collision and use that to solve this problem. So initially, if you're playing pool, the 8-ball is stationary. You don't hit moving balls when you're playing pool. So the initial velocity of the 8-ball is just going to be 0. And I'll use a subscript of 8, so you know it's the 8-ball. And then I'll use a subscript of C for the cue ball. And the little I is just telling us that it's the initial value rather than the final value. So this is the most general statement we could write. Just take your mass, multiply velocity for each object initially, so before the collision, and then finally after the collision. We said that the 8-ball is not moving in the beginning, so this will be 0. The cue ball, the initial velocity of the cue ball is what we're trying to find. We want to know what the initial speed or velocity is. Then they tell us that the 8-ball is going to travel in the positive x direction at 2 meters per second. So 8-ball, final velocity, 2 meters per second. And the mass of the cube, or the 8-ball, is 0.16 kilograms. So multiply mass times velocity, and we get momentum. The cue ball's mass is a little bit bigger than the 8-ball, 0.17. And we want the cue ball to move in the opposite direction as the 8-ball, so it's going to have a negative sign on it, and then it's going to be moving 0.5 meters per second. So negative 0.5. And that has to equal the mass of the cue ball, 0.17, times the initial velocity of the cue ball, which is what we want to solve for. So you can plug this into your calculator. This is positive 0.32. This is negative 0.085. And then to get the initial velocity by itself, we just divide both sides by 0.17. And so when we plug that into the calculator, we'll get what velocity we need to hit the cue ball at in order for us to make the shot and not scratch on the cue ball. So when you plug that into your calculator, you get about
1.38
meters per second. So that's the initial velocity you need to hit the cue ball at to make this shot. So let's revisit that car and large truck having a head-on collision. And now we're asking for the change in velocity of the car in comparison to the truck. So is it the same change in velocity as the truck? Right. So the force that they feel is the same, but because the car has a smaller mass, it's going to have a larger change in velocity compared to the truck. So that's kind of what your intuition might have been telling you already. I know the car should feel something bigger than the truck, but it's not the force it feels that's bigger, it's the change in velocity that it feels that's bigger. The next conservation law that we're going to talk about is conservation of angular momentum. So in physics, almost everything that you learn for things that move in straight lines or linear motion will have an equivalent principle for things that are moving in circles or on curved paths. So conservation of angular momentum is one of those things. So the capital letter L is angular momentum, and angular momentum is just some distance r cross or multiplied by the vector for momentum. So this cross product is a special type of multiplication, but that's not something we would do in this class. That's something you would see in a physics or a math class. And just like so conservation of momentum said that if there's no external forces, then your momentum is conserved. Conservation of angular momentum says if there's no twisting forces, which are known as torques, then your angular momentum has to be conserved. The Earth is orbiting the sun, and there's no torques being exerted on the Earth, and so it continues to rotate on its axis and orbit the sun, and it doesn't cost any energy to do that. So conservation of angular momentum is why the Earth can continue orbiting the sun, why the moon can continue orbiting the Earth. And we'll see some more applications for conservation of angular momentum in a second. We've already talked about one consequence of conservation of angular momentum, and that was Kepler's second law. So Kepler's second law said that as something is orbiting, especially in this elliptical orbit, it will sweep out equal areas in equal times, or as this object gets closer to the sun in this elliptical orbit, its orbital velocity will increase, and then as it gets farther away from the sun, its orbital velocity will decrease. And so this is also a consequence of conservation of angular momentum. And the easy way to see that is by setting up another conservation of momentum statement. So now it's conservation of angular momentum. So we have this equation for angular momentum, m cross v cross r. And I'll put initials on all of those on the initial side. And then I'll put finals on the other things for the final side. So when a planet is orbiting the sun, does the mass of the planet change, or does the amount of material inside of the planet change? No. So the initial mass and the final mass are equal. So we'll just call that m. So now the only two variables that can change are velocity and radius. We said as you get closer to the sun, your radius is going to decrease. So let's say your R final, so this is going down. So the mass isn't changing. If this R value is decreasing, then the velocity value has to increase to compensate. Because whatever's on the left side of the equation has to equal the right side. So if I decrease the R, velocity has to increase so that this equal sign is still true. So that's one of the ways you can use these conservation laws to do some quick conceptual kind of problems. If I decrease one variable, I know that the other one has to increase to compensate. Or vice versa, for the farther away from the sun, my R value is increasing, and so my V value has to decrease to compensate. So if the two things are multiplied together, if one goes up, the other one has to go down. And so a more concrete example that you might have seen in your everyday life, if you've watched the Olympics, you might have seen figure skating. And in figure skating, they do these fancy spins where, depending on the orientation of their arms, they can speed up or slow down. And so we can demonstrate that today. So I don't have ice skates, but I have a platform that I can stand on that spins. And I'm going to hold these weights just to make the effect more pronounced. Let's see. I'm going to start in close, start myself spinning a little bit. And then when I push my arms out, I slow down, pull them back in, and I speed back up. Slow down, speed up. And I'm not touching anything, right? I'm just changing the configuration of the weights in my arms with respect to my body. I'm going to stop that before I make myself sick. So let's revisit that spinning with this conservation of angular momentum. So again, I'm holding extra mass, but when I go in and out, my mass isn't changing. So my initial mass and my final mass are the same. So the R value is changing though, right? If I have my arms spread out, the weights are far away from my body, so R is increasing. And then the velocity has to decrease. So see it again. Start myself spinning. Spread the weights out, slow down, bring them back in, speed up. And so we saw both examples. So increasing radius, velocity went down. Or if I decrease the radius, velocity has to go up to compensate. There's another neat angular momentum demo. This one is a little bit beyond the scope of this class, but I still think it's cool. And if you want to learn why this one works, then you could take an introductory physics class. Okay, so this one, I'm going to start this bicycle tire spinning. I'm going to stand on the platform. I'm not moving. Just by turning the wheel, I can start myself spinning really fast, and then I can just stop on a dime by rotating it back the other way. So this is also a consequence of angular momentum, and this has to do with the vector nature of the angular momentum. So when something is spinning, its angular momentum points perpendicular to the circle that it's spinning on, and so by rotating this wheel, I'm changing the direction of that vector, and that causes me to spin different ways. So there's a couple different things you can do. You can start spinning and make yourself spin the other way, or like I did, you can start from a stop and make yourself spin just by rotating the wheel. And this actually has some interesting applications for satellites. So if you have a telecommunications satellite in space, it needs to beam its signal down to Earth. But what if it somehow ends up pointing not towards the Earth? How do I make something in space point where I want it to? So they have internal gyroscopes, which are just fancy versions of these, where if I turn them in specific ways, I can make my satellite rotate and point where I want it to. Because there's no friction in space, so there's nothing like on the ground I can just move my feet and turn whichever way I want. But in space, there's no friction to do that, so you need gyroscopes and conservation of angular momentum to make that work. Okay, so we talked about conservation of momentum, conservation of angular momentum, and now we'll talk about energy and conservation of energy. So one of the ways you can think about energy is what makes matter move, but there's also other kinds of energies besides the energy of motion. Energy is a conserved quantity, so you can transfer it from one form of energy to the other, and we'll talk about what the different forms of energy are in a second. Unlike momentum and angular momentum, energy is a scalar, so there's not a direction to the energy. We'll represent energy with a capital letter E. It has units of joules, which we represent with the capital J. And it's made out of kilogram, meter squared, and second squared. So these are kind of the three types of energy that we'll talk about in this class. So we have kinetic energy, which is the energy of something moving. So Ke, that's 1/2 mass times velocity squared. There's radiative energy, so that's the energy from light. We'll talk about light more in a few weeks, but all of the energy, not all of the energy, but the energy coming from the sun is in the form of light energy that hits the Earth. And then there are various types of potential energies. So there's chemical energy. So when you do your chemistry experiments and mix chemicals together, that energy you get out of those reactions was stored in those chemical bonds. There's nuclear potential energy. So that's how the sun generates light. And then there's gravitational potential energy, which is the energy that you get when two masses are spread apart from each other. And we'll come back to talking about this today and later next class. But you're not just stuck in this type of energy, you can convert it from one form to another. So plants absorb sunlight, they turn that light or radiative energy into chemical energy to do their life processes. We eat that chemical energy to power our bodies, to maybe turn it into kinetic energy to go for a bike ride. And so you are always transferring energy from one form to another. there's thermal energy, which is you can think of it as heat energy. And it's related to temperature, but it's not the same thing. So temperature is a measure of the average kinetic energy of the particles in a substance. So a lower temperature means that, so if we think about a cube filled with gas particles, like this room, for example, if the temperature is low, the gas particles are moving very slowly through the room. And if you have a very high temperature, then those gas particles are moving very quickly through the room. But it's not just gas that can have a temperature. So solids and liquids are also all made of particles that are moving at various velocities. Okay, so now this is my little rant or diatribe about temperature scales. For this class, we're going to use Kelvin, which is the superior temperature scale. The way you devise a temperature system is you pick basically 2 points of interest, and you assign those points of interest a temperature or a number on your scale. So for Fahrenheit, when Fahrenheit, that's the person it's named after, came up with his system, he picked about the coldest day he experienced was 0 degrees, so he called that 0 degrees Fahrenheit. And the human body temperature is about 100 degrees Fahrenheit, and so he called that 100. So those are the 2 temperature points that he selected. When Celsius developed their temperature scale, they set 0 to be the temperature when water freezes, and 100 to be the temperature when water boils. The problem I have with Celsius is, so some people think setting 0 for freezing and 100 for boiling makes more sense, but those are really only true at 1 atmosphere of pressure and only true for water. So yes, on Earth we have about 1 atmosphere of pressure and we have a lot of water, but other places don't have that. So in my opinion, Celsius is just as arbitrary as Fahrenheit is. And Celsius is less good at measuring outside temperatures. So you have a much smaller temperature range, and so 1 degree of change in Celsius actually can cover like a big range of how something like a room would feel. If I increase the temperature of a room by 1 degree, I might go from it being too cold to already being too hot. But Fahrenheit is a much finer temperature scale, and so I can achieve more precise changes in temperatures with a smaller degree of change, basically. But for this class, neither of those are important because, like I said, they're both arbitrary. So what if instead we picked something that was not arbitrary at all and set that as our 0 point? So that's what Kelvin did, and that's what the Kelvin scale is. We said that temperature is the average kinetic energy of particles moving. So that means that if there's no motion of particles, then I would have 0 kinetic energy. So what if I set that to be my 0 point on my temperature scale? So 0 Kelvin is the temperature where any motion of particles will stop. So that's absolute 0, and you're not going to get temperatures below absolute 0. Then instead of making a whole new temperature scale from the 0 point, Kelvin just said, what if I use the same change in temperature as Celsius. So a change of 1 Kelvin is the same as the change in 1 degree Celsius. So the two temperature scales are just offset by this 273.15 Kelvin. But yeah. So anyways, we're going to use Kelvin for this class. So how are thermal energy and temperature different? So here is an example of those two things being different. So thermal energy is going to depend on not just the temperature, but also the density of the substance that has that temperature. For example, if I have a pot of water that I'm trying to boil, when it gets to the boiling point, all of the water will have a temperature of 100 degrees Celsius, and it won't exceed that temperature until all of the water boils away. But I can heat my oven to, say, 200 degrees Celsius, so that's twice as much temperature. But if I were to dare you to stick your hand in the pot of boiling water or in the oven, which one would you be more willing to do? Yeah, you can stick your hand in an oven that's 200 degrees Celsius just fine. Don't touch any of the metal stuff that's in the oven, but your hand would be fine. But if you stuck it in the boiling water, I would have to drive you to the emergency room. So don't do that. So this pot of boiling water, even though its temperature is lower, because there's more particles in it, it has a higher thermal energy. And that thermal energy is what's damaging your hand when you stick it in the pot of water. So thermal energy and temperature are not necessarily the same thing. Okay, so then the next type of energy we're going to talk about is gravitational potential energy. And so today we're going to talk about near the surface of a planet. Next time we're going to talk about the more far-reaching, like what happens when you have gravity between planets or the sun and a planet. But near the surface of a planet, it just depends on the object's mass, the acceleration due to gravity, and the height above the ground. And we're going to use those different types of energy to feed into conservation of energy. So energy is not something that you can create or destroy in the universe. You can just change it between different forms or between objects. And so if you have some isolated system, say for example the whole universe, then the amount of energy in that system has to stay the same. But as we'll see in a second, you can switch it between, say, potential energy to kinetic energy. So in this example, someone is throwing a ball up in the air, so they're giving it some kinetic energy because it's moving. Once they release it, they're not giving it any more energy, and so that kinetic energy is being converted to potential energy until it reaches some maximum height. And then from that maximum height, it converts all that potential energy back into kinetic energy as it goes towards the ground. So energy is kind of a parallel way of thinking about physics that gives the same result as when we talked about forces and the kinematic equations. So you can also think about this as the force of gravity is pulling down on this ball, and that gives it an acceleration that causes it to fall towards the ground. So both ways of thinking about this situation yield the same results, but the math and some of the nuances are a little bit different. And this potential energy is going to come back in astronomy when we talk about how things like stars form. So it turns out that space is not completely empty, and there are these clouds of gas out in space. Something will cause that gas cloud to start contracting, and as it contracts, it's converting gravitational potential energy into thermal energy. And so I have a lot of things that are spread really far apart, so they have a lot of gravitational potential energy. Bring them close together, and that energy has to turn into something, and what it turns into is thermal energy. And if I heat up a pocket of gas enough, I can make it start doing nuclear reactions and form a star that way. So this conservation of energy is going to be very important when we start talking about star formation later in the class. Okay, so let's see an example of conservation of energy, like a mathematical example. So let's say I throw a ball straight down from a height of 20 meters above the ground with an initial velocity of 10 meters per second. What will the impact velocity be of the ball when it hits the ground? So this is going to be another conservation law, but this time it's going to be conservation of energy. So whatever energy I start with is going to be the same amount of energy that I end with. So I could have some initial kinetic energy, I could have some initial potential energy, and then I could have some final kinetic energy or some final potential energy. So remember, kinetic energy, 1/2 mv squared. And we'll just do potential energy for gravity. So it has this lowercase g subscript, mgh. The initial kinetic energy, they told us we're throwing it down at 10 meters per second. So there is some initial kinetic energy. We're starting at a height of 20 meters above the ground, so there is some initial potential energy. We're trying to find the final velocity, so we want to know what this final kinetic energy is. And then we're finding the velocity right before it hits the ground, so we're calling the ground a height of 0. So if you plug 0 into this equation, you just get 0 potential energy. Because there's a lowercase m in all of these, the mass will cancel out. Solving for the final velocity, multiply both sides by 2. And then take the square root. And then just to be mathematically very rigorous, when you take the square root of something, you should put a plus or minus in front of it. And then you plug in your numbers. Initial velocity 10 squared plus 2 times 9.8 times the height, which was 20. Plug that into your calculator, and you'll get a velocity of 28.3 meters per second. And I'm going to make it negative. I'm going to pick the negative sign because I threw something down, so its velocity is going to be going down. So it turns out so we did this with conservation of energy. We could have also done this with kinematics equations. And if you do it with the kinematic equations, you actually get the exact same result. So, like I said, both kind of independent ways of thinking about the same problem that end up at the same result. the last type of energy that we're going to be talking about is the mass, or the energy that's stored in mass. So this is something that Einstein came up with, E equals mc squared, and it's what governs the energy released from nuclear reactions, whether that be in the center of stars or in nuclear bombs or nuclear power plants, etc. So because you're multiplying the change in mass by the speed of light, which is what c is, and squaring that, the speed of light is already a very big number. It's 3 times 10 to the 8 meters per second. And then I'm squaring that, so that makes it an even bigger number. That means actually a very small change in mass can result in a very large amount of energy released. So in the cores of stars, we'll talk about how that's the energy of just going from hydrogen to a helium atom is not a large change of amount of mass, but it does release a lot of energy. And you might be wondering, okay, we talked about conservation of momentum and angular momentum and energy, but what does that mean? What are these conserved quantities? And Emmy Noether she didn't discover the conservation laws, but she discovered the kind of theoretical framework for how you find these conserved quantities. And so if you're interested in that, you take a lot of high-level math and high-level physics classes, and eventually you'll learn how she was able to derive those conserved quantities. So conservation of angular momentum is what keeps a planet rotating. We'll talk about conservation of momentum when we talk about how disks form, like around Saturn or around planetary systems that are forming. Conservation of energy is one way to do physics, and you just convert between kinetic, potential, or other forms of energy in order to solve those kinds of problems.